bad guys. You know what I mean? What's that called? Got trigger finger.
Trigger finger?
Yeah, you got to hit a trigger. Right. You're shooting everybody. All right? You got to know when you can apply these things. All right, the second form of the fundamental theorem. It's attempting to say the same thing in a slightly different way. And that is, this process called antiderivative undoes derivatives. And so to the other direction, a derivative undoes an antiderivative. That's all it's trying to say. So d dx, a derivative applied to an antiderivative, right? But this is a little more peculiar this time. From a until some unknown x. This is an unknown here. Unknown. And a is any constant. It doesn't matter what it is. Any constant there. Okay? If you apply the derivative operator to an antiderivative operator, but the upper one has to be variable, or one of the, let's say it different. At least one of the two must be variable. Right? What is there nothing to talk about? Of f of x dx f of x. All it says they undo each other. That's all it says. The derivative undoes the integral. Just like here, this says f prime equals little f, right? F prime equals little f. So what does this one say up here? This says integral operator undoes what? Undoes f prime, undoes the derivative, and makes it back into regular f, right? That's what it says. What does this one say? It says the opposite. It says the derivative undoes the antiderivative operator. Right? It's just saying it from both directions. The difference here is you have this little unknown up here. What if this had said b? What if it was from a to b? How would the derivative impact that thing if that was not a variable? So I want you to understand it has to be a variable, or one of the two has to be a variable. What if it was just a to b? Regular case, a to b.
0.
0. Why?
Constant.
It's constant. What is it? What is it? What is a definite integral? A number, right? It's some number. What's the derivative of any number? 0. So this thing's meaningless if I put a b up here. It has to be this is variable.
Oh, so you take the derivative of everything then. So the antiderivative of the integral cancels out, the a cancels out, d of x cancels out, and you're just taking f of x.
Yeah, that's one way, yeah. Alright. So let's try that. We got a couple examples here. Number 51. Applying the second part of the fundamental theorem. It says d dx of integral from 3 to x. 3 to x. Oh, they caught me though. Right, I should have used different letters here. Sorry about that. They're all dummy letters. They're all dummy variables, but I should be more careful. The book uses it like that. It's more proper. T squared plus t plus 1 dt. T squared plus t plus 1 dt. Yeah. All right. So I'll give you something like this. So it's going from 3 to x, and now you want to apply your derivative operator to that, so it should absolutely undo whatever the antiderivative is doing. So the answer should simply be x squared plus x plus 1, right? It is just the variable replaced in the integrand. That's all it is, because they're going to undo each other. We left with that function, the original function. Okay? That's what part 2 is trying to say. Now they're going to try to trick you a little bit. So I'll give you number 54 now. Because that's just ridiculously simple there. So you can maneuver the pieces around a little bit. So they have d dx of x squared to 10. X squared is not just x. It's not just variable x. It is x squared. So it is a function put inside your limits of integration. dz over z squared plus 1. dz over z squared plus 1 is saying the exact same thing. And I actually tend to write it this way when I do problems myself. 1 dz is what it's trying to say. Okay? But the book will consistently put the dz in the numerator when there is just a 1 there instead. Just like this. So I want this to appear like this expression down here. It needs to be from constant to variable. So I'll switch limits of integration. And what do you say? I will negate it. That's right. Remember our rules for antiderivatives, the same as the rules for the definite integrals, is that when you switch limits of integration, you have to tack on a negative, right? We said that last time. That was one of the rules. So we can take the negative outside the whole thing, actually. So we'll have negative d dx, and we'll switch to 10 to x squared. So at least we have the variable part. It's not just x, though. We have the variable part as the upper limit of integration. So it conforms to the second part of the fundamental theorem. Okay, so the other problem now is there's x squared instead of 2x. So this is going to be a chain rule, okay? It's a kind of subtle chain rule you might not have expected to happen. So now when you take the derivative of all this, right, it's going to be negative because of that. This expression with what? With this put in for z, right? So like over here when it was x, where are you? X, we put an x for t. Okay, so now it's x squared, so everywhere you see a z, you're going to put x squared. So we'll have 1 over x squared to the 4th plus 1. But now I've got to multiply by the derivative of the inner function.
Why is it to the 4th?
Because I was already computing in my mind, that's why. Sorry about that. Then I have to multiply by the derivative of the inner function. What's inner in this case? What did I just do? What's inner? The x squared, that's right. This piece right here, the variable part of the upper limit of integration, right? That is the...
So the whole thing's
times 2, x. So derivative of, see, I'm doing everything like advance here. X squared, there. That's what we got to do. So that's one small subtlety that can come up if it's not just x, but a function of x. You've got to take its derivative and tackle on the outside due to chain rule.
What's the d?
Chain rule.
What happened to the d? Where? This dz?
Yeah.
Nothing. You don't have to worry about it. That's just telling you what variable you are integrating with respect to. Just like this tells you what variable that you are differentiating with respect to. Okay, so multiply by 2x and we have our answer. So negative 2x on x to the 4th plus 1 is that answer. Any questions about the second part of the fundamental theorem? How to apply it? That's probably your worst case. The one we just did is probably the worst case scenario, where they switch limits of integration and give you a function.
Easy one.
Do what?
Another easy one.
Easy one?
No, do another one that's gonna be on the test. Don't give us something that we're not gonna be testing on.
I mean, you just doing this?
Yeah.
All the same.
All the same.
Why wouldn't you go further?
Go further. House?
Maintain the quotient.
No. Because you're not taking the derivative of